So now we can start. I hope that everyone who's really interested is already there. The other ones can join later. Welcome to today's Tech Talk. My name is 𝗀𝗲𝗍𝗂. I'm part of the Tech Labs Aachen management team. And I'm really happy that we could win the Research Center Jülich for today's Tech Talk on a really interesting topic. Our speaker is Daniel Zeuch. He will give us an introduction to quantum computing and tell us almost everything about it. Thank you for being here, Daniel. I'm already excited. And Daniel is accompanied by 𝗀𝗲𝗍𝗂𝗏, who is HR manager at the Research Center. And she will give us a short overview of the Research Center and also some career options. Before I hand over to you, I would like to ask you to fill in a really short survey on your current position, because that helps us a lot for statistical purposes. And of course, it's anonymous. And René, you may trigger the survey. That would be awesome. Okay, thank you, René, and thank all of you for participating, or nearly all of you for participating in the survey. I don't have to say anything more about the recording, but still I want to encourage you. We will stop the recording before the discussion, so it would be really nice if you turn on your cameras if you have questions, because that's a lot better for Daniel or 𝗀𝗲𝗍𝗂𝗏 to ask questions, to talk to a real person. That would be really nice. So feel free to do that. And if questions arise during the talk, please put them in the chat. We will collect them and then we will pass them to Daniel and 𝗀𝗲𝗍𝗂𝗏 afterwards in the discussion. And yeah, they will all be seen. Be aware of that. And that being said, 𝗀𝗲𝗍𝗂𝗏, Daniel, the stage is yours.
Thank you, 𝗀𝗲𝗍𝗂𝗏. I hope you can see the presentation now. Yeah, okay, that works. So yes, I would just like to give you a very brief overview of Forschungszentrum Jülich and who we are looking for. So at Jülich, we have three main research topics, which are information, energy, and bioeconomy. And within the field of information, we focus on information processes in natural and artificial systems. There are, for example, our institutes of neuroscience and medicine focusing on brain research, and also everything related, or nearly everything related to computing plays a very important role. So there's super high performance, neuromorphic, and also quantum computing, which you will learn about more in a few seconds or minutes. And within the field of energy research, our aims are to limit climate change and to contribute to the energy transition. And we have institutes that conduct basic, others conduct application-oriented research. And some important keywords are, for example, batteries, photovoltaics, fuel cells, hydrogen, atmosphere, and climate. And the field of bioeconomy deals with the bio-based economy, and our institutes of bio and geosciences are divided into the sections for biotechnology, plant sciences, agrosphere research, and bioinformatics. And who are we doing this with? We have more than 7,000 employees, and many of them are scientists and doctoral researchers from very different natural engineering and computer science disciplines. And in addition to the subject-specific knowledge and that depends on the area and the position, we are also looking for people with curiosity, enthusiasm, and motivation, stamina, the ability to work in a team, and of course also English language skills, because the work environment is quite international. And if you ask yourself how you can contribute to our research during your studies, you can join for an internship, a bachelor or master thesis, or a student assistant job. And afterwards, the classic entry is mostly doctorate, but there are also opportunities besides. And if you have any questions, I will be very happy to answer these later. But for now, I would like to hand over to Daniel to give you an overview of quantum computing.
All right, let me share my screen. File, yes. Okay, now I would like to turn on my laser pointer. I did practice that, so I'm assuming you can see the laser pointer and the mouse.
Yes, it works.
Nodding. All right, so yeah, thank you very much to Tech Labs for giving me the opportunity to give a talk about quantum computing research at the Forschungszentrum Jülich. my name is Daniel Zeuch, and I work at the Peter Grünberg Institute number 12, which is a theory institute for quantum computing analytics. So let me say first a few words about myself. I have done quantum computing research in many or in several different places. For instance, at the University of Konstanz in Germany, and at Florida State University in the United States. And since 2016, I work at the Forschungszentrum Jülich. And I won't go into the details because they will take a long time. So I will discuss mainly the following topics. First, I will introduce the general area of quantum technologies to you, one of which is quantum computing. And then I will focus on this computing part, and I will first discuss some of the basics. Then I will go into the applications and finish with the research activities here in Jülich. So I like to say that we're currently living through interesting times in which the second quantum revolution is taking place. And this, of course, has been preceded by the first quantum revolution in the previous century, in which quantum group effects have been used to develop technologies such as the transistor radio or the laser, but perhaps most importantly, the digital computer. And here in the lower left, we see a picture of one of the best computers that's currently out there, a supercomputer, which is operated here at the Forschungszentrum Jülich, at the Jülich Supercomputing Center. And in the upper left, we see a picture of a CPU. So the second generation quantum technologies, they are based on the manipulation of single quanta as opposed to groups of quanta. And the technologies are quantum sensors, quantum cryptography, and quantum computers. And here in the lower right, we see a picture of a particular quantum computer, which is a superconducting quantum computer, inside a cryostat or a fridge. And we see that it, of course, looks very different from the classical computers that we know and love. And in the upper right corner, we see a superconducting QPU. So that's a quantum processing unit, which looks not so very different from the CPU at a first glance. So then I would like to point out that there are many developed countries that have realized that quantum technologies harbor a lot of potential. And so they have invested large amounts of money into this field. And I think the numbers speak for themselves. This slide is also to point out to you that I'm not the only one who speaks about quantum computing or quantum technologies. So now let's talk about the computing part itself. And one of the first questions that you may ask is, what's new in the quantum computer? And at the very basic level, the main difference between a classical and a quantum computer is the smallest unit of information, which in the classical computer, of course, is the bit, which takes one of the two values, 0 or 1. And here I choose to represent this bit using an arrow, which points up in the case of 0 and it points down in the case of 1. In the quantum computer, one then uses the quantum bit, which is abbreviated as qubit. And this thing can be in a superposition of the states 0 and 1, which loosely speaking means that it's in the states 0 and 1 at the same time. And I choose to represent this state, or this qubit state, also by an arrow, which now points to the surface of a unit sphere. The north and south pole of the sphere are basically the classical states, 0 and 1, and all of the other states are these quantum superpositions. And one important thing in quantum physics is now that we can measure the state of the qubit, and we will find that it is sometimes in the state 0 and sometimes in the state 1. So we will find each state with a certain probability. And one way to picture this superposition is to look at a thought experiment called 𝘀𝗽𝗲𝗂𝗏 cat, which has been the idea came from Erwin Schrödinger, who was one of the founders of quantum physics in the beginning of the previous century. And the basic idea is that here we have a cat which is at the same time dead and alive. And I'm sort of assuming that most of you are a little bit familiar with this thought experiment. And in case that's not the case, then you're welcome to ask me questions about this in the discussion session. But now the advantage that a quantum computer has when by employing qubits is that it can consider multiple solutions at the same time. And so one example is if you want to drive by car from, let's say, Aachen to Berlin, then a quantum computer can look at multiple routes at the same time and thereby come to a solution faster than a classical computer can do this. And with this, I have already told you something about the first application, namely finding shortest routes from one point to another. But there are really many potential applications for the quantum computer, and I would like to talk about that at least a little bit. So the idea about the applications is that all of those things are potential applications which are based on computationally hard problems. And so there are many economic fields which are, let's say, which might be interested in employing quantum computers, and I would like to give you some examples. So one is that of developing batteries, and here a quantum computer can simulate quantum systems and thereby gain an exponential advantage in computing power. And you might wonder what's the relationship between developing batteries and simulating quantum systems. Well, to find better batteries, we might take a computer and simulate different chemical compounds and then evaluate which ones have particularly nice properties in terms of energy storage. So here we see one example of such a chemical or complex compound. And now the difficulty in simulating these chemistry large molecules is that quantum mechanics has to be taken into account. And so where does quantum mechanics play in? Well, for example, in the bonding. So consider this hydrogen atom, which is bound to the neighboring carbon atom. Then this bound is a quantum mechanical bound, which has the feature that the electron that belongs to the hydrogen is at the same time at the place of the hydrogen atom and at the place of the carbon atom next to it. And this is a quantum mechanical superposition. And it's very difficult for the classical computer to simulate this, since the classical computer works with bits, which can be only in one of the two states, 0 or 1. However, for the quantum computer, it is very natural to model this because it employs qubits, which are completely used to being in such superpositions of 0 and 1. And I don't think I have to motivate these days why we would like to have improved batteries, of course. A similar application is that of developing medication and vaccinations. So here we're looking for molecules which do two things at the same time. One, they have to attack a certain virus, but at the same time they should not attack our human body cells, right? And so what we would like to be able to do is predict protein folding, meaning look at certain molecules and then predict what they end up in. And here, once again, quantum mechanics is involved, and for the same reason as what I said earlier, quantum computers can lead to or can have a exponential advantage in computing power. And there's one more such thing that I would like to point out. There's the question of carbon capture. And we know that nature has already solved this problem. It knows how to do photosynthesis, and it gets energy out of the capturing of carbon dioxide. And we are trying to do something similar, we humans. So we build carbon capture facilities to filter carbon out of the air. But in this case, we have to use energy to make this happen. And there is research. I have found this particular article by our Argonne National Lab in the United States, which says, like a leaf, new ways to capture carbon from the air. So we're trying to copy what nature has been doing for a long time. And to understand how this works on a molecular level, it would be, once again, useful to have a quantum computer at hand. And I should point out that not only governments have realized that quantum computers have a lot of potential, but a lot of big companies have realized the same thing, which is why they invest a lot of money and try to set up their own quantum computers. And here I have listed some of them, and you may realize that none of these big players comes from Europe or Germany, but nonetheless, Germany is also trying to build its own quantum computer, and that's what I wanted to talk about at the end. So we in Jülich are one of the few places in Germany that actually try to develop their own quantum computers. So here we see a number of researchers who work in the field of quantum technologies. So these are the principal investigators. Of course, there are many more students that work on the same things. And now here we see a cut of those people who work in particular on quantum computing. And this is still a pretty large number of people. So I cannot tell you about the research of every single one of them. But I can tell you at least a little bit, and I can try to give a bit of an overview. The research efforts can be divided into basically three main broad categories, which are theory, experiments, and applications. And I'm going to start with the theory part. So the one example in the theory department is I have worked together with my postdoc supervisor, Professor David DiVincenzo, on a theory that describes the interaction between light and qubits. And this is relevant because light is something that is actually being used to drive quantum computing, or to make quantum computations happen. And but this is a very fundamental theory. So this is really to better describe what happens in a quantum computer. PGI. So, and this was in PGI 2. So that's another theory institute. PGI 8, on the other hand, takes a more active role in quantum computing. So they do something that's called quantum control. And so they look at very specific quantum gates, and they then look for ways to minimize qubit errors. Okay, so that's all I'm talking about in the theory part. And now I can tell you about experiments, and there's a bit more to talk about. So we have, for example, PGI 13. In case that got lost, I should probably quickly remind you that PGI stands for Peter Grünberg Institute. So this is an experimental institute which does hardware implementation. And what we see in this picture is, so this is a picture of the laboratory in PGI-13, and the cylinder that is hanging here, that's the cryostat. So that's the quantum computer that's the part of the quantum computer that is cooled down to extremely low temperatures. And when I say it's extremely low, then I actually mean very close. So these temperatures are very close to the absolute zero temperature. So minus 273.14 degrees Celsius, something like that. And then we have an engineering institute, which is called ZTA2, and they work on cryogenic circuit engineering. So what they take is they take classical control chips and they try to make them work as good as possible in these with these extremely cold temperatures. And what I didn't point out here is that the hardware that is used by PGI-13 is the same as that Google and IBM and many other quantum computing companies use for their systems. So these are so-called superconducting quantum processors. But we also work on other types of quantum computers. For example, there's PGI-11, which is partly located at RWTH Aachen, and they work on qubits that are based on electron spins. These quantum computers are lagging a little bit behind in the current technology point, let's say. But if we manage to make them work a little bit better, then they will have some advantages compared to the superconducting qubits that we have seen so far. And then there is PGI-9, and they work on a totally different type of quantum computer or type of qubits. These are based on topological insulators, which is a very fancy material. And these qubits have not been realized at all. So this is a little bit up in the air. It's not clear if it will ever work at all, but there are of course high chances that it will. And if we manage to make them work, then these have an even bigger advantage over all quantum computers that we have at the moment. And then I should perhaps mention the biggest hardware projects that are currently present at the Forschungszentrum Jülich, which include multiple institutes. So for example, the Peter Grünberg, many Peter Grünberg institutes, the ZTA2 Institute, and also the Jülich Supercomputing Center. Most of them they are part of these projects. And so one project is called Open Super Q, which started in 2018, and it has a budget of 10 million euro, and we have realized a 6-qubit quantum computer, which, and from what if I remember correctly, then this project is actually finished this year, and sort of the continuing project is called 𝘀𝗽𝗲𝗿. It has a significantly bigger budget, and the promise is to develop a 30-qubit quantum computer in the next 5 years. Okay, and then the next part that I will talk about is applications. So here I will first talk about the PGI-12. That's the institute that I work in. And so one thing that we do is we develop software for control and calibration of current hardware. And this is necessary because the quantum computing operations have to be very precise. And the hardware changes a little bit over time. So every few days you have to recalibrate the quantum computer. if you want to use it for high fidelity operations. So this is one of the things that we work on, and we also work on precise or on specific applications. For example, in a project together with the automobile industry, which is on so-called quantum artificial intelligence. So here the idea is that quantum computers can be combined with the idea of artificial intelligence. And by doing this, the hope is to improve things like the navigation of self-driving cars and the avoidance of traffic congestion. Maybe you could notice that some of the partners are among the 3 biggest car producers in Germany. And yeah, so this is a project that has started about a year ago, and it has another 2 years or so to go. And then I should also not forget to talk about the Jülich Supercomputing Center, which is usually abbreviated as JSC. So here the idea is to they try to increase the potential of quantum computers by combining these computers with the supercomputer, which they operate here on site. And this is really in particular with the current quantum computers, which are still very small, meaning they have a small number of qubits. For these, the combination with the supercomputer might be a total game changer. So it's very good that we have the supercomputer at the Forschungszentrum Jülich. And then one of the other important things that they do at the Jülich Supercomputing Center is they give access to quantum computing resources via a platform called 𝘀𝗽𝗲𝗁. And this access is to people at the Forschungszentrum, but also to outside people. And maybe you have heard of the D-Wave quantum annealer. So we also have such an annealer on site, which is sometimes referred to a kind of quantum computer, but it works a little bit quite different from the quantum computers that I talked about so far. So with this, I come to the end, and I hope I have given you some sort of an overview over at least some parts of the quantum computing research that's going on here at the Forschungszentrum. And with this, I come to the end. Thank you very much for your attention, and I'm glad to take any questions or listen to any comments that you might have.
Thank you very much, Daniel. That was really interesting, and it was roughly on time, so you made it. Thank you for that. I have seen that there are currently no questions in the chat, but I'm pretty sure, yeah, there is already the first